a human-inspired artificial neuromuscular prosthesis. In this work, we propose a prosthesis which was directly inspired by the functionality of the human body. The human body is equipped with a model of its kinematic and dynamic model, called body image. Consequently, we also equip our prosthesis with an artificial body image which provides a model about kinematics and dynamics. This means the prosthesis is aware of its orientation in space as the human body. This comparison shows that the control algorithms, the spatial orientation sensors, joint position and joint torque sensors, have a direct correspondence to the human body. Let's have a look how our body is understood according to the state of the art in human motor control. It is assumed that the motor command of our muscles is generated by a feed-forward and a feedback term. These are generated by a dynamic model and a feedback controller. It is expected that a state estimation is present in the human body, which takes into account effort measurements and model outputs to distinguish disturbances on the human body. Inspired by the prior human analysis, we present a mechatronics concept of a prosthesis which replicates the behavior of the human neuromuscular system. The figure shows which sensors, actuators, and control algorithms were used to obtain a corresponding technical solution to the human body. In this work we show that this mechatronics concept will provide human-like characteristics. More specifically, our human-like characteristics are body awareness, contact awareness, human-like contact response, and human-like kinematics. We first have a look at human-like contact response with zero stiffness, which is depicted in the video in the lower left corner. We see that the human arm maintains its position when being pushed away by gentle interaction forces. Two mechanisms have to be present to obtain this behavior in the prosthesis or the human respectively. A dynamic model provides the correct joint torque for gravity compensation, such that the arm maintains its position. While human muscles are backdrivable by design, we emulate this behavior by joint torque control in the prosthesis. When including a feedback controller, or in other words, an impedance controller, the stiffness can be adjusted to arbitrary values. When we talk about body awareness, we mean the floating base dynamics model of the prosthesis, which provides joint torque and base ranges for the contact-free case. When we talk about contact awareness, we mean the ability of the prosthesis to estimate joint torques, base ranges, and contact ranges for the contact case. The contact awareness can be simply seen as an update of the body awareness for the contact case. This is realized by a disturbance observer, a static model, the floating base model, and joint torque measurements. Explaining body awareness. Here we see the prosthesis ANP with its body image. We see the base range and the joint torques of the floating base gravity compensation model. Explaining contact awareness. When contact awareness is active, the prosthesis is programmed to estimate the external contact range Fx. As a consequence, base range and joint torques are updated according to the magnitude of the external force. Apart from the estimation of base and contact range, multiple contacts are not considered in this work as these are hard to realize via the proprioceptive measurements of the device. Mechatronic device. Here we see the researcher wearing our artificial neuromuscular prosthesis ANP. For the sake of mechatronics evaluation, we control the prosthesis joints via a smartphone application. The choice of the human-machine interface is arbitrary. We rather focus on a human-inspired system behavior which is independent from any human input method. Please note that pilot studies with impaired users are not the focus of this work. The specialty of the ANP is the 4 degrees of freedom, torque-controlled and human-like kinematics, which comes along with human-like size and human-like weight. The prosthesis consists of custom-made elbow and forearm joints and a custom-made tendon-driven wrist. Modular hands may be attached to the prosthesis, which is the SoftHand Pro 2 by QB Robotics in this case. The ANP is supplied by 24-volt DC and is connected to a real-time computer via an Ethercat bus system. A full integration of computation and battery may be achieved by further reducing the size of forearm and elbow joint, as these provide more than enough torque in the current version. In conclusion, we have a prosthesis with human-like dimensions, human-like weight, human-like kinematics. We have joints which are fully torque controlled, which contain custom-made actuator modules and custom-made torque sensing, also for the wrist. We have an IMU in the base for base orientation measurement and can attach proprietary modular hands. All in all, the prosthesis was designed in a sim-to-real design approach, which will be further discussed in the paper. Let us have a look at this user control test, where we see how the prosthesis performs together with the human and the smartphone. The prosthesis can also lift objects of daily living, showing performance of the device. This video shows the maximum flexion of the wrist in 2 directions. Experimental results. In the following experiments, we evaluate the prosthesis in terms of body awareness, contact awareness, human-like kinematics and human-like contact response. Here we evaluate the full Fordorf kinematics via sinusoidal motion. Human-like contact response. Here we see the human-like contact response, where we change the stiffness of the device from high to low and to zero stiffness. For zero stiffness, essentially only a gravity model is active, which is floating base even though the device is fixed. We implement joint limitations as in the human body. Body awareness. Here we see the first prosthesis with the floating base gravity compensation. The system can be guided by gentle interaction forces and resides on its joint position despite the changes in the base orientation. This is only possible due to an artificial body image which runs in real time on the controller. Please note that we fixed the Cartesian position of the prosthesis base, as this information is not available in our sensor design. Contact awareness. We can also estimate an external wrench and its effect on the structure. Even though the device is fixed, floating base models are used. We can use the same technique to monitor and limit harmful moments on the prosthesis attachment, which may be interpreted as an artificial pain reaction. Grasping. Furthermore, we evaluate the mechatronics of the 4DOF prosthesis device by grasping experiments. All tests were performed successfully. Grasping with guidance. Finally, we propose a novel grasping strategy with which we guide the floating base control prosthesis to the object. In this work, we presented the first prosthesis, which aimed for replicating the system behavior of the human neuromuscular system. We showed that the human-inspired mechatronics approach also provides the expected human-like behavior, further specified as body awareness, contact awareness, human-like kinematics, and human-like contact response. More information may be found in the belonging paper.